So the the syllabus, I don't think anybody had a problem accessing that. It'll be in this folder right here that says syllabus and course materials, and then the quiz would have been in here. It says assignments, and then right here, YouTube pop quizzes. So I see that that's visible, and then it should have been this first quiz right here, video pop quiz one, Enantiomers and Chirality. I might have given you like the wrong title in the actual announcement, but it was the only. I think it's the only quiz in here that's actually visible to students. So make sure when you go back, just double check, go on assignments, and then go into YouTube lecture pop quizzes, and then you should see that quiz, and you'll be able to take it now if you watch the videos, and especially after today's class. And then there's the other folder in here that's important. Let me go back to assignments. Assignments, boom, right here where it says in class handout submission. That's where you're gonna turn submit your work. I still need to figure out how to add a submission link to these to the handouts. But this is the first handout for the class right here. It says Stereochemistry in class assignment one. Let's see, it should pop up. And I can't see what you see on your end, but I don't see a submission link. But based on what I see over here, there must be a submission link in with that assignment. I have to open it this way. I just want to make sure that it's the right handout. Yep, it is. So this is the first handout that we're gonna be working from. We're gonna start working from it today, actually. So which again, Blackboard is this Ultra is new to everybody. So just kind of we'll be patient with me. I'll be patient with you, and then we're just gonna make it work. All right. Anybody have any questions before we get started? All right, I'm gonna share my iPad and we're gonna go to work.
I got a question, Dr. Russell.
Go ahead.
Do you feel like we need to print out all the handouts, or do you think we should handwrite it?
If you can do it digitally, it's fine. Um, like I use an app on my iPad called Notability, and I just take notes like that. So if you can edit them digitally, then do it that way. Otherwise, you can print it, or I don't really recommend that because it's a lot of paper. But if that's what you got to do, then it is what it is. Zoom, it's coming. I think. Jeez, oh Pete, man. All right, there we go. Get that out of the way. Let me check this. Let me check this. Go ahead, Brittany.
Can you hear me?
Mm-hmm.
Okay, so I can't see the PDF in the assignments tab you was in. I don't see the PDF of the assignment.
All right, I have to go back and figure out why that is because I can see it from my end, but if it's on the student end and you can't see it, then it's kind of pointless. Let me go back.
It's in course documents and supplemental handouts. It's not in the assignments tab if you want the actual document.
Yeah, it should be, but it should be here too, though. So I'll have to figure out why that. Like you can see it. Let me reshare and show you what I'm talking about. I need to be able to open this from the student view, and then that way I can see what's what. But I don't know how to do that yet. Like right here, you can see Stereochemistry in class assignment 1, spring 2018 PDF. So it's there. I just don't know why why you're not able to see it. Let me see something.
Oh, for some reason, it's just a submission. It's not really the actual PDF, but the PDF is actually there, but it's in a different Dropbox.
That's weird. Yeah, it should be here with
You have to press the 3 dots and then you have to download it.
Oh,
Yeah, that too.
yeah. Okay. Yeah. Yeah. Because I mean, even I can't just click it and open it. I had to do the same thing. Let me see if there's anything over here that I can change. I don't think so. Definitely don't want to add a passcode. We got enough problems already. Oh, come on. I don't like this new Blackboard. I'm just gonna be straight up.
I don't think anyone does.
Some of it is easier to use, like the interface is easier, but everything else is all scrambled up. It just gonna take some time, but we're gonna work together. Like I said, even if I have to create like a big folder in OneDrive and share it with y'all, I'll do it that way, or Google Drive, however that makes. All right. So let me go back to my iPad, and then we're gonna start. We'll worry about Blackboard later. Why they would do that now in the middle of COVID is beyond me. Might be something you want to do over the summertime, but not now. But who am I? Just a lowly professor.
Dr. Russell,
Yes.
I have some questions when we get into configuration.
Okay. Hopefully, I'll answer them before we even have to ask them. But okay, that's fine. All right. So today we're going to talk about. Make sure we're still recording. Yes. All right. So we're going to begin talking about chirality. And out of that concept, we're going to talk about a bunch of different things. We're going to talk about, and let me do something right quick. We're going to talk about out of this configuration. And what that is either R, or if you watched the video last night, you probably already saw, or whenever I sent it, you probably already saw this part about the R and S configuration. And that's just the 3D orientation. Right, that just tells you the 3D orientation of a stereo center. Let me fix that up. All right, and then we're going to also talk about out of the, before we can even assign configuration, we need to know about how to assign priority. Right, and that's based on those CIP rules I was telling you to look up the other day. And we'll talk about that, and then we'll talk about the different types of stereoisomers. We're going to talk about enantiomers, and then diastereomers. Right, those two types of stereoisomers are a consequence of chirality being present in the molecule. And then after we talk about that, we're going to talk about how chirality affects reactions. Sorry about that. Right, so chirality and reactions, and that's a general principle that guides that. And I'll show you real quick. So if you take something that's achiral or doesn't have a chiral center, and something else that's achiral, and react them together, then what you get is what's called a racemic mixture. And we'll explain what racemic mixture means, all that stuff. So some two achiral things, you react them together, you get a racemic mixture. And then I thought I added another page in there. Let me add a page right quick. All right. And then if you take something that's chiral plus something achiral, then it's going to give you an unequal mixture. Right. We'll talk more about that when we get to it. But all of these ideas come out of this concept of chirality, right? So chirality, and anything that contains a chiral center is going to have a specific configuration. And in order to determine the configuration, you have to know the priority of your groups, which we're going to work on a little bit today. And then as a consequence of chiral centers being present, you can have what you call enantiomers or diastereomers, which we're going to talk about. Hopefully you watched the video and this is not foreign to you. And we're going to talk about those reactions. So if you watch the video that I sent out, somebody tell me what, excuse me, what the criteria are for chirality.
This is Brittany speaking.
Mhm.
They have to. It has to have 4 different substituents.
Okay.
It has to be non-symmetrical.
Mhm.
And sp3 hybridized.
So 4 different. Let me make sure I qualify that, because you're right. 4 different substituents. That matters. If you got any two of your substituents are the same, then the symmetry, you'll have some symmetry, and then that kills the chirality, right? So you got 4 different substituents as a consequence of it being sp3 hybridized, right? Because the hybridization state is going to determine how many groups are attached. If it's sp3, it's going to have 4 groups. If it's sp2, it's going to have 3 groups. If it's sp, it's going to have 2 groups. And then it's non-symmetrical, which is a consequence of having 4 different things attached. I'm using a new stylus, so bear with me. Non-symmetrical, and the mirror image is non-superimposable. We're going to talk about that in great detail. Non-superimposable. That word sounds like a lot, but what it actually means is that you can't lay the mirror image and the original image on top of one another and get all the atoms to line up. That's all it means, right? So like, it's like if you took your left hand, I got to turn my video back on right quick. It's like if you took your left hand and right hand and did this, and then you took your right hand and tried to lay it on top of your left hand, right? Nothing matches. The thumbs don't match, index fingers don't match, so on and so forth. So that's what that term means when you hear that term, non-superimposable. It sounds intimidating, but it's really not. Let me fix this before we go on.
Question.
Go ahead.
Is non-superimposable similar to like when we were talking about steric interference?
Not really. Because the thing about steric interference is that you can't avoid it. Right? If you have a something that's causing steric interference, that's just based on its size. It's not based on the configuration. Well, let me take that back. let me say this the right way. So when you're talking about something being non-superimposable, that's not something that has to happen. It's a criteria for chirality and it's a test for chirality, but it doesn't necessarily happen. But if you have something that creates steric interference, that's going to happen regardless, right?
Okay.
Yeah.
Right.
Does that make sense?
Yes.
Okay. All right. So you got these are your 4 criteria, and if any atom, carbon, nitrogen, silicon, sulfur, like you can have other atoms that are chiral centers. If any atom meets these 4 criteria, and I'm gonna just put a quick example down here, then that atom, I'm gonna use carbon, is considered chiral. So I'm just gonna write the tetrahedral depiction of carbon. Right, so you got these 4 groups, 1, 2, 3, 4, like that, right? And so any atom that meets that criteria of being non-symmetrical, of being sp3 hybridized with 4 different groups, and the mirror image and the original image can't overlap, then it's considered chiral, and this is considered a chiral center. Right? You're probably asking like, what's the big deal about chirality? Why does it matter? Um, let me do something real quick, just to kind of make the point as to why chirality matters. Let's see. Actually, I don't have to do that. I can go back. So I'll just pull up the first example, and then we'll make it make more sense. All right. So let's pull up this. Let me pull up this first example right here. Can everybody see that molecule, that big monster of a molecule? The molecule is called paclitaxel. It is actually the common name for it when it's used for chemotherapy is Taxol. Right? It's a very common chemotherapeutic. If you'll notice, we're going to go through this and pick out all the chiral centers. But if you'll notice, like this thing, all these chiral centers kind of give it a shape, right? You see how that's wedged, right? I mean, dash right there and wedge right there. And we got this being wedged, and this is wedged, and this is dashed. So that actually gives Taxol a shape. And because it has a shape, that means that the receptors that it needs to bind to, whether it's in a cancer cell or wherever it's bonding, it'll fit. And if it fits, then that means it's more bioavailable. That means it can do its job, which is to cause apoptosis in cancer cells, right? But if any one of these chiral centers is different, then it's going to change the fit in that receptor. And if that happens, then it may not be as effective. A great example of that is Prozac. Let me see if I can find that right quick, and I'm gonna show you. If I can find the structure of it, I'm gonna show you what I mean, and because that paclitaxel may be harder to see. The Prozac structure is fairly simple. Let me see here. Perfect. All right, let me share this with you, and then I'll show you exactly what I'm talking about. All right, can everybody see my screen?
Yes.
So if you look at Prozac, let's do this. Which what do you see any chiral centers in Prozac? Let's see. Let's see if we can apply that definition of chirality. Let's look at every atom. Right. What about this carbon right here? You think that's chiral? Why or why not?
No.
Don't be scared.
No.
Come on, say it loud. Be black and proud.
I don't think so.
I
No.
want to say no.
It's not. Why? What's the first criteria?
The substituents
sp3
are
hydrogen.
different.
You got to have 4 different groups attached, right? But here you have 3 fluorines, and so that means that that atom can't be a chiral center. You following?
Yeah.
Yes.
All right. What about in the ring? Any of these carbons in the ring chiral?
No.
Why not? What's the consequence of having 4 substituents? The hybridization state is what?
SP3.
3, right? And these carbons are all what? Come on now, bring back that working knowledge from part 1.
SP.
Let me get there.
SP2.
All these carbons are sp2, right? So none of them can be chiral. Same with this ring right here. All right, what about oxygen? Can oxygen be chiral? What's missing in this drawing that's not shown?
I guess the hydrogens, I guess.
Hydrogens or lone pairs?
Lone pairs, sorry.
Yeah, you need 2 lone pairs. And those lone pairs are groups, right? So if you got 2 lone pairs, that means you got 2 of the same group. So that can't be chiral. Does that make sense?
Yes.
All right. What about these 2 carbons right here?
No.
They're both CH2s, aren't they? So you got
Yes.
2 of the same groups, so that can't be. You see how easy it is to identify the chiral centers, right? The identify them is the easy part. Figuring out the configuration is a little bit more difficult, but we're gonna do that too, right? So you got a nitrogen here with a lone pair, a hydrogen, and 2 other different groups on it. So that nitrogen, there's certain instances where nitrogen can be chiral, right? But we're not gonna worry about that right now. We're gonna stick to carbon. What about this carbon right here? Is it chiral or is it a chiral center?
I think so.
It's not chiral.
No.
Okay, what's the criteria?
It has to have 4
4
attachments.
different constituents.
Does it have 4
It only has 3.
Come on, you said 3?
It only has 3.
What's not shown? This is a skeletal form, right?
Right. Oh, it does.
You got a hydrogen that's not shown, is that
Not
right?
shown. Right.
All right. So is that center chiral, or can it be chiral?
It can.
All right. Let me put that on the iPad, and we're gonna talk about it, and we're gonna use that example to talk about configuration too. Go ahead. I heard somebody get ready to ask a question.
So you said it needs 4 different constituents to be
a chiral center.
So
Yes.
if it's attached to 2 different carbons, that doesn't make it not chiral?
No, because the carbons are, let me show you. That's a great question too. Let me draw this thing out first, and then we're gonna talk about it. I'm gonna change.
Okay.
So come on now. We got things to do. I'm talking to my stylist. I'm just gonna draw the ring like that. All right, let me share my iPad again, and then we got 43. That's good. I'm proud of y'all for coming back. Let me share this again right quick, and then we're gonna look at this Prozac. Does anybody know what Prozac is used for?
I know it's a type of
It's a drug used to treat
drug for treatment, or like some type of pain medicine, I want to say.
No, it's actually used to treat depression. Yep, it was very popular in the early 2000s. Now people just grow weed at home and smoke it. Not knocking it, nothing against it.
It actually still works pretty.
Yeah, people still use it, no doubt. It came to prominence in the early 2000s, but people definitely still use it. But for now, let's look at. Let me copy this because I want to show you something. Yeah, people definitely still use it. Oh, come on. I'm gonna paste it here. I don't want the image, I want the real deal. So I want to be able to alter it. All right. So with Prozac, what you see is a couple of things. Number one, this carbon right here in the middle is a chiral center. That's actually a hydrogen on that carbon. So what I'm going to do is I'm going to make this line right here wedged. I'm going to darken it. And I'm going to put my hydrogen on a dash like that. Following?
Yes.
All right. And then on the other image, I'm going to change that line to a dash in the front. And then I'm going to make the hydrogen wedged. All right. Do you see the difference?
Yes.
So these two compounds are what we call enantiomers. They are mirror images of one another.
Could you explain why it's an enantiomer one more time?
Why is a mirror image?
Yes, like it's because of the flip of the hydrogen from being a wedge
That's
to
exactly right. The
atom.
chiral center has the opposite configuration in the second image. Right. So if this is the first image right here, this is 1 and 2, that chiral center is the exact opposite. So that's why they're mirror images. It's just like when if you look at, again, if you look in a mirror and well, let me not say that. If you hold your left hand and right hand up, it's like those, and you have them facing one another, it's like they're looking at each other in the mirror. But when you take it out and flip it over, you can see that it's the reverse. It's not identical. So enantiomers are just that. They are mirror images of each other. But in order to have enantiomers, you got to first have a chiral center. So we've identified the chiral center in Prozac being right here. Is that right?
Yes.
Mm-hmm. So if I have one chiral center, and that gives me a chance to make another point too. If I have one chiral center, then I'm going to have at minimum 2 stereoisomers. Let me write that down here. You need to remember this formula. Right, so the number of stereoisomers possible for any compound is 2 to the n. Right, well, n is the number of chiral centers. All right. Any questions about that? We're gonna do this more, but this was a good place to introduce it. All right. So we got one stereo center, so 2 stereoisomers, and they happen to be mirror images of one another. Right. The reason why this is important is because one of those isomers doesn't work. If you take it it's used to regulate depression. So if you're taking the wrong isomer, the wrong stereoisomer, that means that when you take that drug, it's not going to be effective. That's why chirality is important, because every drug that has chirality has to fit into a specific receptor. And so if you have the wrong stereoisomer, it's not going to fit properly. And it's the same thing with something as simple as Prozac. All right, so let me show you real quick, because somebody asked a question. I think somebody was asking about two carbons being attached. Who was that? All right, we'll come back to it. So let's go to some other examples, and let's see if we can pick out some chiral centers. And then once we do that, we're going to also start talking about what the mirror image and all this stuff. We're going to use another example to do that. Talk about enantiomers and then diastereomers. All right. So question, here's a question. I want you to think about this and calculate it. How many, you're gonna hear me use chiral centers and stereo centers interchangeably too. So both of those terms are interchangeable. How many chiral centers are present in Taxol? Let's see if we can figure it out. What can we rule out on Taxol? And before we go there, there was the organic chemist, what's his name? I can never remember his name. I want to say Hoffman, at Florida State. He patented the synthesis of Taxol. And when he patented the synthesis, he sold it to, at the time, Bristol Myers for like $2.5 million plus royalties. And the reason that's important is because of where this actually comes from. It's actually a alkaloid that comes from the Pacific yew tree, but it takes 100 years to grow one tree. From the bark of it, it comes from the bark of the tree, but it takes 100 years for one of those trees to grow. And even if you harvest the bark from one tree, you're really only gonna get enough Taxol to treat one patient. So being able to synthesize it was important. Being able to synthesize it with all the right stereochemistry was even more important. So again, organic is like you have to do a lot of things right in order for a molecule like this to actually make it to the market. They call this like called translational research, where you go from the bench, to the bedside or to a hospital bed, right? So let's see if we can figure out what we can rule out. What can we rule out?
Maybe the aromatic.
All the aromatics, right? None of those carbons are going to be considered for chirality. Anything sp2, we rule it out. Do you see any other sp2 carbons? About right here. Can we rule out that double bond?
Yes.
Can we rule out all carbonyls?
Yes.
Because they're all sp2, is that right?
Yes.
We can every carbonyl, every pi bond, we rule it out. What else can we rule out? Can we rule out all the CH2s?
Yes, because that's
And
sp2.
we can rule out all the CH2s and CH3s, right? Because they all have multiple substituents that are identical. Is that right?
Yes.
Yeah, so we can rule that out. So we'll rule out this CH2, rule out that CH3, this CH2 right here.
Dr.
Go ahead.
Why didn't we take off the one like towards the left that has a double bond on oxygen?
Towards the left, you mean right here?
No. Go like straight across.
Okay.
Well, not all the way, but like,
The
okay.
one that's connected to the OH.
Yeah.
Oh, right here. I missed it. You're talking about this one?
Yes.
Yeah.
Thank you. Anything sp2 hybridized and any CH2 or CH3, we're going to rule out as a possibility for a chiral center. All right. Am I missing any CH2s or CH3s? Yes. Right here, right? That's a CH3, so that's out. Am I missing anything else? Right here. And this carbon too, right? Because it's connected to two CH3, so that's not going to be a candidate for a chiral center. Are we following that or no?
Yes. Well, why would you that last CH3? Why would you exclude that one?
It's a CH3. It's got 3 hydrogens, so it's got 3 of the same groups.
Okay.
It's got to have 4 different groups attached to it in order for it to be considered a chiral center. All right. So where are my chiral centers? Let's see if we can figure that out.
I was gonna guess, I'm not exactly sure, but maybe the part with that OH, that
Yeah,
seems like,
this one is a little easier to kind of decipher because all your chiral centers, they got them labeled. They give them a direction, right? It's either wedged or dashed. That's what those wedged and dashed lines mean. Like it's either wedged is coming out of the page and dashed is going back into the page. So that's the chiral center right there. That's one. This is one. There, there. Let's see here. Are y'all following that? Here, here. Both of those are chiral centers, and then that's a chiral center.
does that happen every single time with the wedge or a dash, or is it
Sometimes it may not, you
sometimes?
may not have it wedged or dashed, but it can still be chiral. Just might not have a direction. The wedge is just telling you that you have a known configuration. But if you draw it on a straight line, it means that the configuration is undefined. But that doesn't mean it's not chiral.
Okay.
Yeah. So the wedge or dash is telling you that it's either R or S, which we can figure out from this example too. We can do that. But I want to talk about the priority stuff first before we do.
Dr. Russell,
Yes.
if you go to like the first chiral center where it's connected to the nitrogen,
Mm-hmm.
are you to assume like the fourth thing is a hydrogen?
Yes.
Okay.
Because if it's drawn in skeletal form, remember, you don't have to show the hydrogens.
Can you explain again what makes it a chiral center?
So it's a carbon or another atom that's sp3 hybridized, that has 4 different groups attached, that's non-symmetrical, and that has a mirror image that's not superimposable on the original image.
Thank you.
Right. Is that what you were asking?
Yes.
Let's look at the one where nitrogen is and we'll make it make sense. All right. So what's the hybridization state of nitrogen? Is it sp2? Is it sp3? It's got to be sp3, right? Because we're calling it a chiral center, right? And it's got 4 different things attached to it. That we're looking at this carbon now, not nitrogen, right? It's got 4 different things attached to it. It has nitrogen. I need to hold up. Let me thin that out some. Right? It's got nitrogen. It's got a carbon on this side. It's got a carbon on this side. And what's not shown is that there's a hydrogen here on a wedge. Is that right?
Yes.
All right. So that's your 4 different substituents and the sp3 hybridization. And it's not symmetrical. So the fact that it's not symmetrical is also a consequence of that is gonna be that the mirror image is not superimposable. So they all those criteria go together.
So, Dr. Russell,
Mm-hmm.
where there's a staircase, there will always be a wedge, or no?
Say that again now. No. Like I just mentioned that a second ago. Sometimes you might see, let me give you an example. What if I had a molecule that looked like this? Right? Those lines are not defined. They look thick, right? But they're not defined. They're just straight lines. But this is still a chiral center right here. And so is that. Right? Even though it's not wedged, the wedge and the dash give you an idea about what the configuration is, whether it's R or S. But it doesn't have to be drawn as a wedge or a dash in order to be a chiral center. Like when it's not drawn as a wedge or a dash, what that means is that we just don't know whether it's R or S. It's undefined. Right? But if you see a wedge or a dash, then you can start looking at that atom and determining whether or not it's chiral. Right? It kind of helps to like make the process a little bit faster if it's already wedged or dashed. But it also helps us to determine the configuration as well.
Can you show an example where it's bonded to the same substituents? Because I think I've seen the one when you had it with the 3 fluorines,
See
but
right
I
here?
just need.
You see the carbon right here?
Yes.
It's got 2 CH3 groups attached to it.
Mm-hmm.
That's an example.
Okay.
Like the CH3 down here. This is an example. It's a carbon here, but it's got 3 hydrogens attached.
But in the other one, then it was attached to 2 carbons, but that's okay. But it can't be.
Which one? The one we just showed?
Yeah.
No, that's not a chiral center. Because the 2 CH3s are identical. It can't have any identical substituents. They all have to be different.
Okay.
That's why we ruled it out. We said that it could not be a chiral center. Make sense or no?
Can you go back to where it's with the nitrogen? You see how on both sides it's 2 carbons? That's what I'm getting confused at.
Yep.
Because those are the same, but
No, but are they the same though? Let me erase the box. So is this carbon right here? Let me use a different color. Is this carbon right here the same as this carbon? They're both carbons, but they're not the same. Can you see that one of them is sp2 and one of them is sp3? That's a difference right there.
okay, yes, okay, that makes sense now.
Yeah. So that's where your CIP rules come in, where you have to understand, even though they're both carbons, like sometimes you'll have a situation where you have a carbon that's bonded to another carbon on each side, but it's still a chiral center. We're going to look at it in there's some examples here in this molecule right here. Are we okay with that so far?
Yes.
All right, so you got that is a chiral, that's one of your chiral centers. Now we can figure out let's go to the next one, and then we're gonna come back and do the configuration if we have time. If not, we'll do it Friday. Let's go to the next chiral center. All right, so this one right here, we can draw in the hydrogen. So that's my 4th substituent. And then again, do you see here how you have this? This is a carbon, and then this is also a carbon, and then it's bonded to oxygen. So those are my 4 substituents right there: oxygen, hydrogen, and then 2 carbons. Anybody not see that?
So all the substituents have to be different except for carbon. Okay.
Say that again.
I said all the substituents have to be different except for carbons. Like
carbon is not an exception, because if you look at the 2 carbons, they're not the same. They're just the same atom, but they're totally different. Like you see the one here is bonded, is sp2, and the one here is sp3.
Okay.
Yeah. So carbon is not an exception. If that was the case, then over here, this would be considered chiral, right? But it's not. So you're looking at the carbon, but you're also looking at what type of carbon it is and what it's bonded to. Does that make sense?
It did.
All right. Let's look at we'll go up here and look at this chiral center right here. What's missing on this one up top?
A lone pair?
Okay, we can put lone pairs in on oxygen. Yep. But what about the hydrogen? Shouldn't it have a hydrogen on it as well? going back. Can you see how if the oxygen is on a wedge, then the atom, the other atom that's bonded to that carbon has to be on a dash, right? So we have a hydrogen going back into the page, right? So where are my 4 different substituents there?
Both of the carbons, the hydrogen and the
Hydrogen and
oxygen.
oxygen.
Got the same scenario, don't you? You have a carbon on this side, you got one on that side, you got the oxygen here, and then the hydrogen here. And these 2 carbons are not the same. Can you see the difference? This carbon has a double bond to oxygen, and the carbon over here, sorry about that, the carbon over here has a double bond to another carbon. So they're not the same. Yes, they're both carbons, but they're not identical. Do you agree or disagree?
I agree.
What about the next chiral center, the one right here? What do you think? Where are your 4 different things?
It's the 2 carbons, a hydrogen, and then the methyl.
Yes. So you have 2 carbons. I got to change my highlighter to a different color. So you have, let me erase this. You got a carbon here. Is that right? A CH3 right here, a carbon here, and you have a carbon on the other side, which happens to be a chiral center, but it doesn't matter. Right here. Right. So those are your 4 groups that are around that, the chiral center that's depicted here. All right, so that's what you're looking for. You're looking for atoms that have 4 different substituents. It doesn't matter if the configuration is indicated or not. If it's got 4 different substituents around it, it has the potential to be a chiral center. Are we okay so far?
Yes.
All right, so let's see if we already picked out all the chiral centers, so let's count them up. We have 1, 2, 3, I think it's 13, 4, 5, 6, 7, 8, 9, 10. Am I missing one? Somewhere. Let me put my purple highlighter back. All right, so we count up all the ones highlighted in purple. That'll give us the number of chiral centers. So 1, 2, 6. Oh, this one should be in purple. And 11. It's 11. I count 11. Is that right?
Yes, it's 11.
So 11. So Taxol has 11 chiral centers. How many stereoisomers are possible? Right? 2 to the 11. Is that right? Because this is how we calculate the number of stereoisomers by taking, it's just 2 raised to the number of chiral centers. So 2 to the n. And then a stereoisomer is what? Somebody help me out. I think that was in the first video I sent.
It has the same structure, but a different 3D orientation.
Different 3D orientation, right? And what gives it the 3D orientation?
Is it by the no?
What are we talking? We're talking about chirality, right? And chiral centers.
Right.
So it's the chiral centers that give it its 3D orientation. All right. So we got a total of 2 to the 11. Somebody calculate that if you got a scientific calculator.
It's 2048.
2048 possible isomers. That's a big number. That's a lot of that. That means that think about the fact that you have a potential for 2048 stereoisomers, but this is the only one that works against cancer cells. So to be able to develop a synthesis of a molecule like this and get one isomer is like the holy grail of organic chemistry, right? And at the end, I'm sure they had to do some type of purification to isolate this one stereoisomer. But yeah, that's not a small feat to have the potential for 2048 stereoisomers, and yet you only end up with this one, right? And every stereo center has to have the proper configuration. So every step in this synthesis has to have you have to generate the right stereochemistry. We're going to talk about that too when we talk about the reactions and how to generate chirality in a reaction. We'll talk about that. Any questions so far? All right. Let's see if we can do something real quick with the configuration, and we're going to talk more about this on Friday. So I'm only going to look at this one stereo center right here with the nitrogen. And so let me not do that. Let me do this. Let me not do that on that. I'm gonna do it over here. All right. So when we talk about the configuration of a chiral center, what we're talking about is whether it's right-handed or left-handed, R or S. So the handedness of it, or the 3D that again is the configuration that gives the 3D orientation of a stereo center. So if it's R or S, that's going to be determined by the priority of the groups. Can anybody tell me what priority is based on?
The atomic mass.
Good. Right. So the atomic mass is how we define or how we determine priority. Right. And so let's jump over to here because we're going to come back to that Taxol example and see if we can go through and determine the configuration of each one of those 11 stereo centers. Right. And then we're going to talk about the mirror image and the diastereomers and the like using that same example. All right, so let me go to right here. All right, so when you're determining the configuration, you have to determine what's called a priority. And again, it's based on atomic mass or atomic number, right? So if I'm looking at, let's say right here, this problem right here, 513A, right? And it's asking me which group has a higher priority. How do I determine that if these two groups are attached to a chiral center? So I'm just going to put a generic atom here, X, and I'm going to attach CH2, CH3 to one side, and then CH3 to the other side. And the question is, which one is higher in priority, right? And the way you determine that is, right, you look at the first atom, which in this case is going to be carbon, and in this case is going to be carbon. Right? And so with that being said, you can't determine it because they both have the same atomic number, the same atomic mass. So you go to the next atom. In the case of the ethyl group, right, the next atom is what? Carbon. Right? The next atom on the CH3 is hydrogen. So though when you compare the carbon and the hydrogen, which one is higher in atomic mass?
Carbon.
Carbon. So that means that this side or this group over here is going to be higher priority. Right?
So you're saying, if I'm getting this correctly, you're saying that just because it has two carbons on that specific side, it has a higher priority instead of the one on the other?
Yeah, you can think about it that way. Yes.
And would this work with other atoms?
It depends. That's why we got some other examples down here. Let's do oh, we out of time. Shucks. Let's do D. I'm gonna stick that over here too. I should just I'm gonna rewrite it over here, and then we'll stop. So we're looking at this one right here. So you have C, right? CH2, CH2Br, and then on the other side it's just CH2Br. You following?
Yes.
So when we look at the carbon on either side of that chiral center, it's the same atom. Is that right?
Yes.
Okay, so what's the next atom on this side?
Bromine.
Bromine, right? What's the next atom on this side?
Another carbon.
The carbon. So which side is higher in priority?
Oh, the bromine.
This side. Are you following?
Okay, that makes sense. I get it.
Mm-hmm. So you just look for a point of difference, and then you compare the atomic masses at the point of difference, or the atomic numbers at the point of difference. So we're going to talk more about this. Say again.
So this is the last one. So basically, you have to stop with the least amount of like atoms on one side. So you can't really count that last bromine on the right because there's only two other atoms on that left side, right?
I don't know if that's a good way to think about that. You're really just looking for a point of difference, right? So when you compare these two carbons right here, right, those are my two carbons that are attached directly to the chiral center. And then they're the same, so I move to the next atom. In this case, it was a bromine. Sorry about that.
Dr. Russell,
Mm-hmm.
Is it okay if we leave if we have another class?
Yeah. I'm done. I apologize for going over.
Okay, thank you.
Yep. And in that case, you have a carbon. So you stop at the point of difference.
Okay, thank you.
All right, we got to stop here because I'm over by 2 minutes, so I apologize for that. I'll post this video to YouTube. I'll post the notes to Blackboard when I figure out how. And yeah.
Dr. Russell, do you have a moment for me to show you something?
Mm-hmm.
Thanks, Dr. Russell. Have a nice day.
All right, y'all take care.
Dr. Russell, bye.
All right.
Can you see this?
Yeah, that's a Fisher projection.
Okay, so I'm confused. Am I counting this and this?
Are you looking for, you trying to figure out like whether it's chiral or not?
The configuration.
Are you looking at yeah. So which center are you doing first? The one that you have circled?
So both of these are considered centers.
Yes. So you have to do them separately.
Okay, so that's okay. I got that part. When I'm doing this one, am I counting this C in the 4?
Yes.
Okay, that was the question that I needed to answer.
So when you compare that C where your mouse is to the other C down on the bottom, the CH3, Go over to the CH3. No, not that one. That one. Yes. You're gonna have to apply those priority rules there, right?
Okay.
Because that carbon up top is bonded to iodine, and then the carbon on the bottom is bonded to nitrogen on one side and then CH3 on the other side.
Okay.
So when you compare those two carbons, that bottom carbon is bonded to hydrogen. Following?
You said the bottom carbon
Yeah, no,
is.
go over back to the CH3. Yeah, that's bonded to hydrogen.
Mm-hmm.
And the other carbon up top that you comparing it to, yes, that's bonded to iodine.
Iodine.
Yeah. So it's
Okay.
gonna be the top group is gonna have a higher priority than the CH3.
Okay.
And it's gonna be the same thing when you do the top carbon and compare it to where the bottom carbon is gonna be a substituent.
Okay. I had one more question about the because I remember it was talking about the 4 priority, which is mostly H,
Yeah.
would be facing us.
Yeah, but okay, so on a Fisher projection, the thing you look for is whether the hydrogen is vertical or horizontal.
Okay.
See, both of these are vertical. If the hydrogen was on one of those other two positions, then it would be horizontal, and then you would reverse the configuration.
Okay.
If it's vertical, you keep it how it is. So let me do the bottom. So the bottom, the nitrogen, put a 1 right there on nitrogen.
This one?
Just write a 1 there. And then 2 is going to be the carbon up top. The one in the middle. Yep. Because that's what's attached to your chiral center. And then the other carbon down on the bottom left is going to be 3. Yep, that's 3. All right. And then the hydrogen is 4 in priority. Right.
Okay.
So if you counted the atoms or counted the groups 1, 2, and 3, it's either going to be clockwise or counterclockwise.
This is counter.
Yeah.
So
So it would be S. Right. And the fact that hydrogen is vertical, you see hydrogen is vertical on the bottom. Yeah, on the one we're looking at. Yeah. So you would keep it S.
Okay.
If hydrogen was were to swap places with the nitrogen,
That way?
it'll be on a straight line just like it is. Don't put
Okay.
it on a dash. Yeah. If you just wrote hydrogen on a straight line, just like you have the NH3 written, if you put hydrogen where the NH3 is and NH3 where the hydrogen is, the configuration is going to change.
So that way?
No, I'm saying, well, it don't matter what side it's on, but if it's horizontal, then that wouldn't be S anymore. It'll be R.
Okay.
Right. We're going to talk more about that hopefully on Friday.
Dr. Russell, can you post this part, a part of the video as well, or is that too long?
It's still recording actually, so that's a good thing.
Okay.
Yeah.
Okay. Thank you.
Okay, y'all take care.
Thank you. You do too.
You too.